I want to show another instance where we can have the effective stress equal to zero that can occur in some situations. What I'm illustrating is an example where we have excavation in clay with underlying sand, and we have some pore pressure in the sand. Situation looks like this. I have water here, so in other words, it could be like San Francisco Bay, and we have the overlying soil is clay, an underlying soil, for instance, with gravel or sand. And our goal is to create a basement for a structure. And the basement is intended to be 18 feet deep, for instance. We have, so the ground level is at 0, water level is at 2, gravel is at 20 to 25 feet. So we start to dig our basement, and we dig our basement to 10 feet. So as we dig this basement now, the question is, will our excavation be dry? And it can be, even though we're digging below the water table. So the water table's at 2, we're digging below that to get to 10. And can the basement be dry? Yes, because water comes out of clay very slowly. So while there is a tendency to fill that excavation with the water, it can't come out very quickly because the soil is clay. So in theory, it can still be dry. In fact, there are times when the water can come out of the clay so slowly that it actually evaporates faster than the water comes out. So the excavation could remain dry. Now the intended plan is to excavate to 18 feet. And what we're going to do is we're going to consider a point A here, which is at 20 feet, and I want to look at the effective stress at point A as we dig our basement. So we have saturated weight of the gravel is 120 pounds per cubic foot, the saturated weight of the clay is 100, and the width B of our basement is 200 feet. So this is t equals 0 minus situation. There we're beginning our excavation. There's our complete excavation. So we're going to be looking at each. We're calling this stage 1, stage 2, stage 3. And what we're going to do is find sigma v prime at the 3 stages. And then we're going to say that B is so big because it's 200 feet. We don't need pressure bulbs to do this. So again, we look at our picture. This is stage 1. I'm looking at sigma v for A, 2,000. Why? Because I have 20 feet of saturated clay at 100. So 20 times 100, 2,000. I'm looking at sigma v for B, for stage 2. So at point A, what do I have? I only have 10 feet of saturated clay, so it's 10 times 100, 1,000. At stage 3, I'm looking over here, I only now have 2 feet. So it's 2 times 100, 200. Now, what is my pore pressure? Now, water is not flowing, so I don't need a flow net or anything like that. So, and I'm looking at the pore pressure in the sand, so I don't have any sort of excess pore pressure or anything like that to worry about. So I simply use my piezometer, my U water table, basically. So it's going to be 18 times 62.4. So I get 1123, and it stays the same at every stage because there's free communication from this water into that gravel, and therefore this water level determines the pore water pressure, 1123 for all the stages. But now so I calculate out what sigma v minus u equals sigma v prime, so I have 877. Then I have sigma v minus u, but what do I see? It's negative 123. And even worse, I mean, it doesn't make any sense. Negative effective stresses don't make any sense. We can have negative pore pressures, but we can't have negative effective stresses. And then it's even worse at stage 3, we're negative 923. What are those negative stresses? That means that the pore pressure is greater than the total stress. Well, if the pore pressure is greater than the total stress, what's going to happen? In other words, this pore pressure comes here, and it is greater than the weight of the overlying clay here. And what does that mean? Well, that means that the pore pressure will cause the ground to break, and we're going to have our excavation filled with water. It just breaks through. It's sort of like breaking through a dam. So in other words, as we start to build our basement, we get down to a certain spot, and you think that we would be, you would think that, in theory, it looks like we could do this, but because of the large pore pressure, we end up filling our excavation with water. Water fills the excavation. So this is an important concept that you need to watch for if you have underlying sand or gravel layers below a clay and you're trying to make an excavation. Okay, getting back to flow nets. Here's a problem that you should be able to do at this stage. And so I've given you the flow net, and the problem is to find UA, UB, UC. So I've got points A, points B, points C. Find the pore pressure of those points. Find the hydraulic gradient for the shaded square. Total flow under the dam. And I want you to find sigma V prime at point C. So in order to find sigma V prime at point C, you have to use the pore pressure at point C. So it's simply the total stress minus the pore pressure. So you have to get the total stress at point C, in other words, account for the weight of all of that is above point C. So it's simply just figuring out the total stress using the unit weights of the soil. Given unit weight of the soil is 125. The permeability of the soil is 3.5 times 10 to the minus 4th feet per second. I'm just saying that the dam is 600 feet perpendicular to the page. I've helped you out a little bit. I drew the piezometer here at A. Oops. And what do I note? That to get to point A, the water has passed through 2 squares. So basically I take 2 squares times 2.5 feet per square, and I get a drop of 5 feet. How did I get the 2.5 feet per square? If you look here, what do I have? I have water level there. Oops, water level. I didn't show it very well. It's supposed to be 35 feet. I'm a little bit off. Well, let me modify that here. This is 35 feet. So my H is 35 feet. I have how many squares? I've got 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 13, 14 squares. So my ND is 14, and so I get H over ND, 35 divided by 14. I get 2.5 feet of drop per square. So I've gone 2 squares, 2.5 feet, 5 feet. So I drop 5 feet for there. All right, that gets you going. So please pause the video and solve for the rest of this problem. Okay, I'm going to assume you've solved it. Here's what we get. Let's look at point B. To go to point B, we go through what? 1, 2, 3, 4, 5, 6, 7.5 squares to get to point B. So my head drop would be from the upper level. I get 7.5 times 2.5. I get 18.75 feet is my head drop for there. To get to point C, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I go through 12 squares to get to point C, and so I go 12 times 2.5. My drop is 30 feet, so I have my piezometer at C, and the drop is 30 feet. So my goal now to get the pore pressures is what? I need to figure out that vertical distance for A, that vertical distance for B, that vertical distance for C. So the vertical distance for A, well, A 75, and then the drop is 5. So in other words, so it's 75 minus 5 for point A. For point B, I'm at 120. That's that total distance minus the 18.75. So it's 120 minus 18.75. For point C, I'm at 82. 82 minus 30. So 82 minus 30. I take each of those, I multiply by 62.4, I get the pore pressures of that amount. Then, so that gives me all my U's. I want to look at I of the shaded square. Well, I of the shaded square, I'm going to note that what is the length L here? So 45 minus 65 is, so this, I need to figure out this distance, the distance the water has traveled. That distance using the measurements given is 45 minus, or 65 minus 45 is 20. So 2.5 feet per square, it's 1 square. Divided by 20, the length that it travels, and I get a hydraulic gradient of 0.125. Then to get my Q, I have to use my Q equation, which is Q is equal to KH N over ND times L. And so the K is given to be 3.5 times 10 to the minus 4th. The H is what? Is the total water level drop. Again, I have my, need to move that a little bit. So I get, I get My H is 35. KH. The number of flow paths is 3. 1 path, 2 path, 3 paths. So I have NF over ND, 3 over 14. My L was given to be 600. I multiply all that out, and I get 1.58 cubic feet per second. So that gives me my Q. My sigma V prime at C, I have to use the U at C, which is 32.45. I get my sigma at C. So at point C, I have what? I have 10 feet of water, and then I have 30, this works out to be 37 feet of saturated soil. Guess I didn't specify what it was. So I have 10 feet of water, 37 feet of saturated soil, minus the pore pressure, and I get 2004 PSF. Okay, here's another one. Same type of problem. I'm going to let you work it, so pause the video, work this problem. Again, the secret to doing these is to draw a piezometer at each point that you're interested in. And I'm not going to go through this in detail, but one of the first things you have to compute, obviously, is the delta H, the drop per square. And so you have to look at the geometry given here, so I'm not going to go through it. We have an H of 28 feet. So I have 28 feet. I have 12 squares total. How do we count the squares? 1, 2, 3, 4. Oops. 4, 5, 6, 7, 8. Oops. 8, 9. Oops. 9, 10, 11. 12 squares. And so we get 28 over 12, 2.3 feet per square. So you get that. Then you can figure out that for A it's 2 times 2.3. For B it's 8 times 2.3. For C it's 10.5 times 2.3. For D it's 11 times 2.3. So we get the head drops, and then you have to use the geometry. I've asked for the hydraulic gradient of the shaded square. Here's the shaded square. Now, I've given a scale here, so this is another way to give this problem. Is the scale is 1 inch, approximately equals 20 feet. Well, I realize you can't use that, but you can sort of sketch out the scale, and you get that the width of that square is approximately 10 feet. So when I do I, the shaded square, it's 2.3 for 1 square. Divide by 10, I get a hydraulic gradient of 0.23. And then you can all plug into the values to get that. At point D, we're going to use the pore pressure at D. But we're just going to, what do we have? We have water, we have soil, and you can all get the sigma V at point D, and then subtract off the pore pressure at D to get sigma V, sigma prime at D. Okay, skip that one. Again, this is just another reminder that sort of our rule of thumb is that when the hydraulic gradient is approximately 1, we're going to get a sigma V prime equals 0. Again, what does that mean? If the sigma V prime is 0, the particles don't have any contact stress, and then we have a soil that's liquefied, a quicksand. I critical approximately equals 1. It's a good rule of thumb. Okay, this is sort of off topic, so I'm going to sort of skip this. All right, our next topic will be soil strength.